Hey, welcome back. Limits at infinity, note 7.6. I know you cannot wait for this day of notes. So let's just get started. Today's goal is pretty simple. We're going to evaluate limits at infinity. So as x increases to positive infinity and as x increases to negative infinity. All right, so we got a couple things going on. So we're going to look kind of at two types of functions. I know all functions don't fall in this category, but I feel like if we focus on these, you can kind of relate everything else to these two. So when I look at this function, because I have a vertical asymptote and a horizontal asymptote, this is considered to be a rational function. So at some point, we had an x in our denominator. So if you look here, you had an x in the denominator. Because the degree of my numerator right here and the degree of my denominator are the same, the horizontal asymptote is the ratio of those leading coefficients. So as x is getting bigger and bigger and bigger, so if we look at this graph and we think, okay, as x is getting bigger and bigger and bigger, what's really happening to this graph? So as I look at this graph, it's going this way, this way, this way, this way, and it's actually getting closer and closer to a specific value. It's getting closer and closer and closer to that horizontal asymptote, which is 1/2. So we could say the limit of the function f of x as x approaches positive infinity is 1/2. And again, remember, limit means approaches. So this does not mean that y equals 1/2, because we all know that if we have a horizontal asymptote, as we go out to the right and out to the left, the graph will never cross the horizontal asymptote. However, it will get infinitely close to 1/2, and that's what this means. So on the flip side, if we come over here and we look as x is getting smaller and smaller and smaller, so we're going this way. So if we get on the graph and we write it out to the left out here, we're also getting closer and closer and closer to the horizontal asymptote. So when I think about what's going on here, y is approaching. So y is approaching. And again, approaching being the key word, 1/2. So we could say that the limit of this function as x is approaching negative infinity is also 1/2. And again, it means y is approaching 1/2 does not mean that y equals 1/2. All right, so this is just a different kind of graph. I don't see any asymptotes. It's actually a continuous function. So this is just a graph. I'm going to call it a polynomial. In this particular case, it happens to be a cubic polynomial. So when I look at this, I can look at the power. My highest power is a cube. So if I jump on the graph and as x is getting bigger and bigger and bigger, I can look at this graph and I can say, okay, well, if I get on and I trace it down, I am getting smaller and smaller and smaller. So when we think about this, what's really happening is we are decreasing without bound. So technically, could we say we are approaching negative infinity? That would probably also be an acceptable answer. So we're approaching negative infinity. So now, if we look at what the graph is doing as x is getting smaller and smaller and smaller, so now x is getting smaller and smaller and smaller. So if I look at this graph as x is getting smaller and smaller and smaller, this time y is actually increasing. So we could say that y is increasing without bound. So we're increasing without bound, and some of you might also say that we are approaching positive infinity, which technically, I guess when we think about it, it's really impossible to approach positive infinity because we cannot put a value on infinity. So I tend to use the words increasing and decreasing without bound. There's no limit to how high or how low my function can go. All right, limits at infinity. Case number 1. Okay, so when we think about this, limits at infinity, this is really for rational functions. So when we think about rational functions, they have a horizontal asymptote. And you need to remember from Algebra 2, depending on who your teacher was, we had a couple cases. We had the dolly, we had the Beyonce, and we had the boring case of no special name, just boring. So if we think about what the dolly means, the dolly means that the degree in my numerator was greater than the degree in my denominator. And when this happens, it means you're a dolly, that you have no asymptote. Okay, so you have no asymptote. There is not one. It does not exist. However, if you are a Beyonce, the degree of your denominator is greater than the degree of the numerator. And then when this happens, your top is bigger than your bottom. Just like Beyonce, your top is bigger than your bottom, and that's where this comes in. When you look at Beyonce right here, y equals 0. So we actually have a horizontal asymptote at y equals 0. So basically the x-axis becomes your horizontal asymptote. And case 3 is technically quite the boring case. So case 3 is when the degree of the numerator actually equals the degree of the denominator. So the horizontal asymptote is the ratio of the leading coefficients. So let's evaluate some limits at infinity. Fun times ahead. B. All right. So when we think of limits at infinity, I really do not care about the whole graph. Okay, so at the end of the day, we do not care about the whole graph. We literally only care about the end behavior. So what's going on at the ends of this graph? So I look at this function, I have to determine what kind of function it is, so what kind of category it's going into. So if I look here, the degree of my denominator, and here's the degree of my numerator. So here, my bottom is bigger than my top. When my bottom is bigger than my top, this turns into a Beyonce, which means I have a horizontal asymptote when y equals 0. So in this particular problem, I have a horizontal asymptote. Let me pick a different color. Maybe it'll show it. When I have a horizontal asymptote right here on my x-axis. So that means regardless of my graph, as x gets bigger and bigger and bigger, the limit is going to approach infinity from both directions. So when I think about what's happening, whether this piece is up down here going like this, or whether it's up here like this, I'm approaching 0. Okay, so right now what's happening in the middle of the graph isn't super significant because to the left and to the right, both of the ends will approach the horizontal asymptote. Remember, it's not going to have both of these pieces, it would have one or the other. But the limit at infinity would actually equal 0 because we are approaching that horizontal asymptote as we go out to the right and as we go out to the left. Okay, so another function, I look at this function and I'm thinking, oh wow, look, I got another x in the denominator. So because I have an x in the denominator, this is telling me that it is rational, so I need to check for asymptotes. So when I look here, the degree of my numerator is 1, the degree of my denominator is 1. So my horizontal asymptote is going to be the ratio of my leading coefficients. So it's going to be the line y equals 2 over 1, or the line y equals 2. So in this case, if I come up here, 1, 2, I have a horizontal asymptote right here at 2. And again, it's not really going to matter what my graph does. I actually have a vertical asymptote at 3, so I'm going to go ahead and draw my vertical asymptote here. But this graph is going to come out here and look like this here, and it looks like this over here. So as I approach positive infinity and as I approach negative infinity, both ends of this graph are approaching my horizontal asymptote, and my horizontal asymptote is at 2. Therefore, that is the answer to this graph. So if your function's rational, both ends should approach that horizontal asymptote, and that would be the answer to your limit. And remember, it approaches. The function approaches. It does not equal horizontal asymptote. All right, so now I am looking at this next function. I don't have a denominator, so that tells me that it's not rational. So this is a polynomial function. And now you have to think of Mr. Roboto from Algebra 2 and think about what is your end behavior doing. Okay, so when I look at this graph and I look at everything that's going on in this equation, I'm basically going to focus on two things. I'm focusing on my degree right here, which is odd, and I'm focusing on this right here, which is negative. The negative sign tells me that my graph is going to fall to the right. So I really don't know what's going to go on here right now, but I know because of that negative that the right end behavior of this function is decreasing. Because the degree, or this overall power right here, is odd, my ends are going to do opposite things. So again, I have no idea what's going on in this middle, but the problem's not asking me what's happening in the middle. It's asking me what's happening at the ends of my functions. So it's asking me as x approaches positive infinity. So this particular time, I'm looking at positive infinity, so I'm going out to the right. And when I go out to the right, this graph is decreasing, so I would simply write decreasing without bound. And that's all you have to do on that one. All right, so we will continue going. All right, again, example number 4, got to look at your function, kind of make some determinations. I don't see a denominator, so there's no variable in the denominator, so this cannot be a rational function, so it's a polynomial function. And again, because I am looking at limits at infinity, I only care about the end behavior of this function. This is not asking me about anything that's happening in the middle. So like, what's happening in the middle of this graph? I don't know, and quite frankly, for this problem, I really don't care. So when I look at this graph, or this equation, excuse me, we have a positive leading coefficient. So that tells me my right end behavior is going up. I am increasing forever. Because the degree is even, that's like touchdown, both ends do the same thing. So both ends do the same thing. So in this particular problem, both ends, whether you're approaching negative infinity or approaching positive infinity for x, we are increasing without bound from both directions. So the answer to this one, we have the same end behavior, so this function is increasing without bound. Okay, maybe we can do something different. Okay, so we have the limit as x approaches negative infinity of 5 minus 2x squared. So here, if I think back to my limit rules, I could actually break these up by the properties of limits. So as x approaches negative infinity of my constant, and then subtract the limit as x approaches negative infinity of this rational function. And how do I know that last function is rational? Because I'm looking at it, and there is a x in the denominator. So if I think of what the function 5 looks like, if I come over here and I graph 5, I basically have a line that crosses the y-axis at 5. So no matter what point I am, because that graph is continuous across the entire domain, the limit as x approaches positive or negative infinity of 5 is simply going to be 5. So that's the easy case. Now I have to determine what's happening in this other case. So if I think about what's happening here, again, I got to think, is this a dolly, a Beyonce, or neither? So I'm thinking my degree on the denominator is 2, so the bottom degree is bigger than my top. And when my bottom is bigger than my top, I have a Beyonce, which means I have an asymptote that comes across as 0. So I have an asymptote right here at 0. And then regardless of what my graph does, this one's actually reflected. And it also has a vertical asymptote at 0 if you want to get picky. So this graph is actually going to look something like this. I am looking at the limit as x approaches negative infinity. Because this has a horizontal asymptote, it wouldn't matter if I am approaching negative infinity or positive infinity. Either way, my y is approaching 0. It will never equal 0. It's just going to approach 0. All right, and 5 minus 0, time for the easy math, is 5. So that would be the limit as x approaches negative infinity of the given function. Okay. All right, let's tackle example 5. So when I look at example 5, it's a little bit different than the other ones in the fact that I have two binomials in my numerator. I am going to go ahead and multiply those binomials together. So I have the limit as n approaches, or yep, it's n in this problem, not x, sorry, as n approaches infinity. And when I go to multiply this together, I get 2n squared minus 1n minus 4n plus 2 all over n squared. So now when I take a peek at the degree in my numerator and the degree in my denominator, they are the same. So my horizontal asymptote is going to be the leading coefficient of my numerator over the leading coefficient of my denominator. So in this case, it's going to be y equals 2 over 1. So if I go to graph this function, regardless of what's happening, I have a horizontal asymptote here at 2. So whether I'm approaching positive infinity or negative infinity, I know that this limit is going to approach 2, y is going to approach 2, regardless of whether I'm going out to the right or out to the left. All right, so when you come to class tomorrow, make sure you come in with any questions you have. You can message me those in Canvas as well. And we will take some time tomorrow to do a quick review over this and work on homework 7, 6 in class. Hope you guys have a wonderful evening. Talk to you later. Bye-bye.